Namaste. Good morning, guys, or good afternoon, or whenever the heck you're watching this. All right. This is Mr. Golis, and I'm here to talk about friction today. All right. So we're talking about friction because friction is a force, and it's a common force. It's all over the place on planet Earth. Now in space, it doesn't really exist that much, but on Earth it exists all over the place. Okay, and it's a force that could either be good or it's kind of neutral. You could, sometimes it's beneficial, sometimes it's not. All right. For example, just we use it all the time when you're walking from place to place. The reason why you can walk is because as you're standing on the ground, there's some friction between the soles of your shoes. And the ground, and when you kind of move forward, that friction, you're pushing against the friction between the soles on your shoes and the ground, and so you're able to use that friction to move forward. And if you to contrast this, imagine trying to walk on something that doesn't have a lot of friction, like for example ice. So if you're walking on a really slick ice surface, you know exactly what I'm talking about. All right. It's the friction between the tires and the road that allows the car to actually go forward. When the wheels turn, they push against the force of friction between the bottom of the wheel and the road, and the car is allowed or is able to go forward. If that friction wasn't there, the car wouldn't move. And you might have experienced this if you've ever been in a car that has gotten stuck, where the wheels just turn and the car's not going forward. Why? Because maybe you're in the mud or you're on some ice or something like that, and the friction, the force of friction, it didn't go to zero, but it went way, way down, and it's not enough for the car to move. So friction can be an important force. Also, with respect to cars, it's the force that actually keeps the car in the curve. So, for example, when you're on a curve, if this is like an exit ramp on I-95 and the car wants to stay in the curve, all right, when you turn the wheel, when you turn your steering wheel, the front wheels turn because of the mechanism, and they increase the friction between the front tires and the road, and it allows the car to keep into the curve. All right, so it's actually friction that keeps the car on the road. All right, if there's not friction, if there's like in the wintertime, let's say you guys know what I'm talking about when I say like black ice, it's like a thin sheet of ice that gets on the road, all right, and it just looks like the road is wet, but it's really not just wet, it's really ice. And if you hit that, what winds up happening is your frictional force goes way down, and it's not keeping the car in the turn anymore, and the car moves in accordance with Newton's first law, which is in a straight line and a constant speed, which normally would be okay, except that when you're in the curve in a straight line, all right, there tends to be a ditch or a guardrail or an embankment or something something that you don't want your car to hit. All right, so friction can be an extremely important force. It can also work against us because it's the reason why when a car is going, all right, you need to constantly burn gas. Why? Because there is that friction between the road and the tires, and that doesn't go away. And as soon as you take your foot off of the accelerator and stop, at burning gasoline in the engine to keep the force up, then that car would start to slow down. In addition to that, there's friction between the body of the car, fluid friction between the body of the car and the air, which can be quite strong. And if you, at low speeds, fluid friction is kind of negligible, but at high speeds, it becomes very, very powerful. And if you don't, if you ever want to test this out, all right, get on I-95 and roll down your window, go about 85 miles an hour, stick your face out the window, and you'll find that the fluid friction due to the air can be quite powerful. All right, so let's start talking about friction and what causes it, and just the nature of it and so on. All right, so friction is caused. Now I want you to do this little thought experiment. imagine if you're standing like on just on the floor in your room or something like that, which, you know, for the most part seems smooth. I mean, it's not like a sandpaper floor or something like that. As long as you're not standing on a rug, you know, like a tile floor or hardwood floor, you know, or linoleum or something. And all right, so it looks roughly smooth to you at your, you know, level of existence. But if you were to shrink down to like the size of a grain of sand on that same exact floor, the floor would look quite different. It would not look smooth anymore, and you would see that what at your normal level looks smooth, really the floor has a bunch of like kind of hills and valleys in it, all right, bumps and so on. So it would be, you know, you would see stuff like this. You know, the floor would take on much more of a texture. Okay. Now, what winds up happening is, so let's say, you know, here's one surface right here. If you put another surface on top of it, okay, that other surface would not be smooth either. In fact, the reality is there is no completely smooth flat surface known to human beings in the year 2020 or 2021 or whatever year I'm showing this video. It doesn't exist. Even if you were to have a surface where the atoms that make up the surface were completely in line with each other, and you know, not one is above the other or not, it still would not be smooth. Why? Because atoms are, you know, roughly, atoms are kind of a weird thing, but you can envision atoms as like these round kind of balls like that, like balls on a pool table. And if you were to rack them up, the tops of the, you know, the surface of the, you know, the pool balls would still not be smooth. All right, because of their shape, they're not flat. All right, so atoms aren't flat. So there is no completely smooth surface known to human beings. So what winds up happening is when you have one surface that is imperfect and not flat in contact with another surface that is imperfect and not flat, all these little imperfections kind of catch on each other like that. All right, and so if you try and move surface one way. Now, each one of those little catches is really, really tiny microscopic force. But if you multiply that by millions, billions, or trillions of times, it can become a very, very strong force. All right. Friction, by the way, for the most part, is still like what stops your car. If you think about it, and this is how strong it could be. So when your car is moving, what happens is when you engage the brakes, all right, you step on the pedal, a hydraulic mechanism takes, you know, some metal brake pads and, you know, jams them together, all right? And what does that do? That creates an immense amount of friction and eventually brings your car to a stop. And to envision how powerful this is, I mean, imagine even if your car is going like, you know, a measly 10 miles an hour down the road and you didn't have brakes and you had to try and stop your car by like sticking your leg out there or something. Good luck with that, all right? It takes, you know, a car has a lot of inertia because it has a decent amount of mass, so it takes a decent force to stop the thing. So when you engage the brakes, it's really the force of friction that's stopping the car, okay, or your bike or whatever the heck. So that's really what's going on there. All right, so this is really kind of the cause of friction, and I want to talk about different types of friction right now. So, and again, make sure you know and write this down that there is no completely smooth surface, because that's kind of an important concept. Okay, so we can classify friction several ways. All right. One, here's my chalk. One is static friction and versus kinetic friction. Okay. All right. So what does that mean? Well, I got this here's an old board. This is a old 1x6 that I had in the shed. I got most of the dirt and stuff off of it, and this is what's called a friction block. All right, so this is all it is a 2x4 that has just a pine surface on the one side, and on the other side we'll staple some sandpaper to it. So here's the difference between static and kinetic. Now, if I move if I incline, okay, good, that's on camera. If I incline this this board, you could ask, well, wait, why is the block not sliding down? Isn't gravity trying to pull it down, to the end of the board? And you would know, like if you're standing on a hill or something like that, gravity kind of draws you down to the bottom of the hill. So why is it not moving? Well, that's because of the friction. That's because of the friction between the sandpaper right now and the top of the board. Okay, good. So, and now before it starts moving, we call this static friction. So this is an example of static friction. Static as in stasis, okay, as in state, all right, which means, stationary, all right, and that's, the root of the word stationary also, all right. So, so when eventually I incline this enough, all right, so that it starts moving, there we go. Once it starts moving, we say that's now kinetic friction. So static is the friction you get before something starts to move, and kinetic friction is the friction that you get after it starts to move. In general, static is greater, and kinetic tends to be a bit less. And you've experienced this if you've ever pushed something, had to push something heavy, all right, so it's harder to get to, so if you have to push move some furniture around or something like that, it's harder to get the object moving, all right, because you have to break that static friction. Once the object's moving, it's a bit easier. You don't have to push as much to keep it moving. Why? Because you're working against kinetic once it's moving, which in general tends to be less. And that's because of the object's inertia, among other things. All right, objects don't want to start moving, so you have to overcome its inertia to get it started. All right, and once it is moving, with the kinetic case, then the object wants to keep on moving, so you have that inertia working with you in the kinetic case. Okay. So that's the difference between static and kinetic. Now, interestingly enough, because I'm doing this for all my classes, but I want to talk to the VOTEC or technical physics class right now. But this is actually kind of for everybody. All right, when you have a wheel on the road, okay, and the wheel is rotating, obviously like a tire or something on the road. What type of friction do you have? Do you have static or do you have kinetic? All right. Now, most people would mistakenly say kinetic because, the wheel is moving. Yeah, no. You would think that, and that tends to make sense initially. But if you think about it more, it's not, because it's a rotational type of motion. All right. And what happens is each point on the wheel that's in contact with the road is instantaneously at rest. It's at rest for a very, very small period of time. So it's actually the friction between the road and the tire is always going to be static. The only time it won't be static, God forbid, is when you start to slide. Okay? So if you lock up your tires to avoid some or whatever, and the car goes forward while the wheel is not turning, then that's kinetic, all right? But while the wheel is turning, you actually have static friction in play that's moving the car, all right? Make sure you know that, especially you VOTEC kids, all right? So, because that's, part of just the mechanism of driving in vehicles in general, all right? Okay, so you have that. I want to talk about other types of friction, okay? To get back to my demonstration, all right? So, I want to make sure I'm in the frame. All right, so this is when you have friction between two surfaces. There's some other ways to classify friction. When you have friction between two surfaces, we have what's called sliding friction, okay? So, this is another way to classify types of friction. So we have three other classifications. One is sliding. And sliding is between two surfaces. Okay. Sliding friction is affected by several factors. All right, one is surface area. Okay, so the more surface area you have between two surfaces, all right, the more friction you're going to get, because friction is a contact force. All right, so the more of those little bumps, all right, between each surface that you can lock up, the more friction you're going to get. So the more surface area you have between two objects, the more friction you're going to get. And that's why, like for example, like if you're into vehicles at all, like racing vehicles, all right, will oftentimes if they're starting off the line, like especially like cars that are like starting like right off the line from zero, okay, like drag racing or something like that, the tires tend to be wider. Why? Because the wider tire has more surface area to it. So if you're starting and you got to get going very fast, you want that friction initially to push the car forward. So you want wider tires. Wider tires, more friction. Now, if you're into gas mileage, you don't want wider tires, because they do create more friction. You want smaller amounts of friction. If you've ever seen like bicycles and like racing bicycles, and their tires are really, really thin, they're like a half an inch wide or something like that. Why? That's to reduce the amount of friction between the tire and the road while you're racing. Okay, so which makes it easier for you to pedal and takes less energy and kind of gives you an advantage. All right, so surface area is one factor. Okay, another factor is how rough or smooth the surface is. So the smoother the surface, the less friction you're going to get. The rougher the surface, the more friction you're going to get. And these are the factors that affect sliding friction. Okay. Another type of friction is rolling friction. Okay. And rolling friction is really like sliding friction except between two flat surfaces. One surface is curved. So here's a roll of duct tape that I got from the basement. All right, and all right. So when I put it on the incline plane, here I have it on the incline plane. So I have. Okay, I'm in the shot. I have the surface. I have a little bit of surface area there, where the circular object meets the flat object. Okay, so rolling friction in general, and make sure you know this, tends to be less, and I'll show you this in a minute. So it tends to be less than sliding. Tends to be, doesn't always have to be, but it tends to be. And here's a good example of this. So here I have so here's the difference between rolling friction and sliding friction. So here's the roll of tape, all right, and I have it on the board, and I'm going to lift and incline the board till it moves. And you can see, so look at the angle of the board right there, okay? Now I'm going to take the same roll of tape and do this with it, okay? And now look, all right? Now look at the incline. So I'm trying to get it, see how easily it moves, right? And I do that, and I have very little incline to get this moving. Why? It's the same object. Well, because this is sliding, and tends to be a lot more, and this is rolling, and it tends to be a lot less, which is why human beings invented the wheel. Again, another example of sliding versus rolling. All right, put your car in neutral and then push it, and you can do it. It takes a bit because your car has a lot of mass and a lot of inertia, but you can do it. Now take the same car, take your car, put it in drive so that the transmission's engaged and the wheels aren't going to turn. All right, and now try and push it, and good luck with that, because now the wheels aren't turning. You're not going to have rolling friction. You're going to have sliding friction. It's rolling friction that actually turns your car. All right, because look what happens here, right? So the wheel's rolling. When I turn the front wheel, all right, because I want to go, in this case, to my right or something like that. If you take a look at it, see which way it's going? Why? Because in this direction is rolling friction, which is less, and in this direction is sliding friction, which is a lot more, which is why, again, ice on the road in the wintertime tends to be bad, all right? Because if you take away the sliding friction, well, there's no disadvantage to going that way, which is probably not the way you want to go, All right, so the car turns, and when you turn the wheel, it goes in the direction of the rolling friction, which is why they tell you never to really lock up your tires. Okay, because if you lock up your tires, as soon as you lock up your tires and stop the wheel from turning, there's no advantage to going this way anymore as opposed to this way. Okay, so Isaac Newton will take over your car at that point, and when you lock up your tires, you're just going to go straight line, constant speed in whatever direction, last direction your car was going in, and that's what happens. That's why they have an anti-lock braking system, which, and if you've ever noticed, if you've been in your car and you step on the brakes hard enough that the car starts to shudder, and what's really going on is the car is the anti-lock braking system is engaged, so that the car locks up and then lets go, and then locks up and then lets go, and then locks up and lets go. Why is that? Well, because you're trying to avoid locking up and then just going that way. Back in the proverbial day when I was learning how to drive, they would say there was we didn't have anti-lock braking systems, and they would say pump your brakes when you're sliding. And the reason is because you're trying to avoid locking up the tire, okay, and so that the tire is allowed to spin, and you might get some rolling there. And you might not have complete control of your car when you're doing that, or when you engage the anti-lock brake system, or when you're pumping your brakes, but you might have 50% control, which if you're about to crash, 50% or even 30% is better than 0%. So, that's the reason for that. Okay. Third type, and I'm just going to mention it. I don't really have much of a demonstration here because I'm just working, out of my house and not my classroom. But the third type is fluid friction. All right, and fluid friction is friction between either two fluids, and by fluids I mean any gas or any liquid. All right, so anything that flows. Right, so the air is a fluid, but also so is water. Gasoline is a fluid. All right, so is helium gas. All right, so anything like that. And when you have fluid friction, it depends on several things. One thing that fluid friction depends on is the speed that you're traveling through the fluid. All right, so the faster you're moving through the fluid, the more the fluid's going to push back on you. Okay, and again, I gave the example a little bit ago of rolling down your window at 80 miles an hour and sticking your face out the window. All right, you're going 80 miles, and if you're walking, people tend to walk at about like 3 miles an hour. You're not really feeling the air push against you. But if you're in a car going 80 miles an hour, then it's really significant. If you can imagine like a jet going 500 or 600 miles an hour, all right, you could not stick your face out that window, or your face would come right off, all right, because of the fluid friction involved. All right. Aircraft, when they travel very, very fast, like faster than sound, like Mach 1, Mach 2, Mach whatever, they actually have to be designed in such a way so that the joints, all right, that make up the plates of the aircraft, the body of the aircraft, where there's a joint, is allowed to, there's some flexibility in the joints. All right, where there's connections between metal plates on the skin of the aircraft. Why? Because when you're traveling that fast, fluid friction will actually heat up the aircraft, all right, to the point where the metal starts to expand significantly. And if you don't allow for that, okay, then the plane, you could have structural failure, which means like the wings will come off or something, which can be inconvenient if you're traveling like Mach 3, okay? And that's just due to fluid friction. Okay, so fluid friction can be very, very significant. Okay, another thing that affects fluid friction is surface area. And I think I'm still in the shot on that, right? Yeah, yeah. Okay, so the amount of surface area you have affects fluid friction. Why? Because again, friction is a contact force. So the more that the body of the vehicle is in contact with the air, the more the air is going to push back on the body of the vehicle. All right, which is why, like back in the day, like if you look at cars from the 1970s, like when I was a kid, they were not designed to be streamlined. All right? We just back in those days, we just didn't really care, right? Like I said, gas was cheap, there was plenty of it. Make a car whatever shape you want, and so we had these cars with a front end that was like flat, and you tend to have a bumper that went like that, and then so you had a hood, and then the windshield went something like that, and your wind tunnel test would just, like go like that, and it was like horrible wind tunnel tests. But we just didn't care. We put a big V8 engine in the vehicle and just burned more gas, and it's like, who cares, whatever. But now, obviously, it's an issue, right? So when they started to when people started to demand lower, or better gas mileage, the engineers had to redesign the shapes of the cars, and that's why today you have cars that have these much smoother shapes than cars in the past. Okay, so, or at least in the 70s was a big decade for like kind of squarish type of vehicles. All right, but that's why you had that sort of thing. All right, it's to reduce drag or fluid friction. All right, it's also the reason why a parachute works, because if you were to like jump out of a plane or something without a parachute, what's going to happen? Well, as you go faster, the air is going to push against you more. All right, and eventually you'll stop getting faster. And that's a concept called the terminal velocity, right? You'll accelerate due to gravity until eventually the air pushes on you so much that even though gravity's pulling down, you're just not getting any faster because the fluid friction against your body is pushing up so much. But the speed at which that happens for an average sized human being is something like 120 miles an hour or something is your terminal velocity. I think I'm being conservative. I think it's more than that, which means that without a parachute, you're going to hit the ground at 120 miles an hour, so you die. But what a parachute does is it increases your surface area. So you deploy the parachute, and suddenly, this sheet above your head has like 10 times the surface area of your body. And what that means is that your terminal velocity goes down in equal amounts. So if the sheet is 10 times bigger than the surface area of your body, then your terminal velocity goes from 120 miles an hour to 12 miles an hour, which is a heck of a lot more survivable. So that's why a parachute works, because of that surface area concept. Okay, so there you have that. Now I'm going to talk about another thing. Okay, and this is called with respect to roughness. Okay, there's a number that we have for every type of surface that kind of indicates, it's an indicator of how rough or smooth a surface is, and this is called the coefficient of friction. And of all my classes, all right, I want the VOTEC class to know this the most, all right? Why? Because you are dealing with vehicles. Now, if you're in the honors physics class, all right, I'll teach you coefficient of friction, and you'll need to know it for my class, but once you leave my class, you'll probably never say coefficient of friction again, or, really even have to think about it, all right? But if you are going to be an automotive mechanic, I think you need to know this, and remember, you're being not just a technician, is what so learn technical language. And what a coefficient of friction is, it's a number that's assigned to a surface, all right, that tells you how rough or smooth the surface is. And it's a number between 0 and 1. I think there are coefficients that are higher than 1, but that's for like substances that are like sticky or something like that, all right? But for the most part, it's a number between 0 and 1. 0 would be completely smooth. Okay? A substance with a zero coefficient of friction would be completely smooth and have no resistance. Where, there's no like surface like this, but this zero coefficient exists in like outer space. Okay, where if you're a vehicle moving through outer space, there's nothing holding you back. There's no air out there. All right, so there's no friction. So space has a zero coefficient of friction. All right, one is a very, very rough surface that causes a lot of friction. So one is rough. Okay, so for example, all right, if we were in class, all right, we would do this experiment, all right, where what we do is we take the friction blocks, right, and we put them on the planks, and we actually measure the coefficient of friction between sandpaper and the wooden plank, and then the smooth pine side and the wooden plank. And every time we do it, we see that the sandpaper has a higher coefficient of friction. In fact, the sandpaper, and I'll just do SP for sandpaper, because I've been doing this for like a quarter of a century now. It pretty much always works out that the sandpaper has a coefficient my students get of about like 0.7. All right, it gets a coefficient of friction of about 0.7, and pine on the bottom tends to get coefficients of about like 0.3, 0.4. So it always works out to be less when we measure the coefficient. It's an easy way to do it, all right, in class, right? That again we would be doing if I were right there. Okay, so that's the difference. So that's what coefficient of friction means. Now, the last thing I want to talk about is the equation. It's the equation that we get for friction. And friction depends on the normal force. Let me draw that a little bit lower. So here's an object, and it's got a certain mass, right? And if I were to do like a free body diagram on this and look at the forces on it, I would have the weight of the object, mg, or its weight going down, and pushing up, I would have an equal and opposite force that we call a normal force. And that's from the slides on forces. All right, normal force is the force of the reaction force of a surface pushing up on something. All right, and friction is actually winds up being proportional to the normal force, okay, of an object. So if you were to make a graph of the force of friction, all right, versus the normal force, all right, you would get a straight line. Now, you're probably saying at this point, like, Golis, you need to clarify this. What are you talking about? All right, you might also notice that the heavier an object is, okay, the more friction you get. So right now, if I take this board right here and I put, it's got, only so much static friction between it and the board. If I put a weight on it, it's harder to pull along. And if I put more weight on it, it would be tougher to pull along. Why? Because what's going on is as you have more weight, the two surfaces right there in contact, those little hills and valleys that cause friction to begin with jam together more. Okay? And so you're probably saying like, well, Golis, why isn't it just proportional to how much you weigh? The more weight you have, the more friction you're going to have between two surfaces. Well, it winds up being proportional not to your weight, but the normal force. And why? Because when you're on an incline, right, your weight is not pulling down this way. It's pulling straight down. It's offset a bit. The normal force is straight up, okay, like this, to the surface. So it's actually, which is actually a little bit less than your weight, all right? So it's actually the normal force that is the more relevant force to talk about with respect to friction. And it turns out that if you were to increase the normal force on an object and then measure the friction it has between a surface, and as the normal force goes up, the force of friction goes up, and it goes up in a straight line. And it happens every single time. no matter what surfaces you use, no matter what objects you use, if you increase the normal force, the friction goes up. Well, what's the equation for a line? Well, it's y is equal to mx plus b, because then some math teacher taught you that. Well, we don't have a y, all right? We have an f on the y-axis, all right? And we don't have an x, we have an n on the x-axis. So n, and b is the y-intercept. That's where it hits the the origin. So, and that would obviously be 0, because if you had no normal force, that would mean that you're not touching the surface and there'd be no friction. So b is 0, so we're not going to even write it. Let me write that n better. And m, that the slope, rather than write m, because we tend to use m for mass, we use the Greek letter for m, which is this funny looking thing right there, which is the Greek letter mu. Yeah, like a cow. Mu is just the Greek, in the Greek alphabet, it's their letter for M, right? And it looks kind of like that. That's a lowercase mu, all right? So the equation for friction is actually, this right here. It's actually F, force of friction on an object. Force friction, I'll put a little F there for friction, is equal to mu times n. That mu right there is the coefficient that I was just talking about. And again, make sure I'm still in the shot there. Yeah, that is the coefficient, which I'll abbreviate, of friction. Okay, so that's a general insight into friction. Okay, I'm going to send you guys some slides on it and stuff like that. But I just wanted to do just a quick kind of lecture on the board and with some demonstrations and stuff. Make sure you have notes on this and that sort of thing, and make sure you know this stuff. Okay, namaste, and goal this out and enjoy your apocalypse.